Okay, let's go and get started with what we're going to get through today. This is class 4, and this is going to be a relatively short lecture, so I'm going to give you time to work on the lab, which is the first lab we've had so far this semester. So in this class, essentially what I want you to do is kind of pay attention to what we're doing here, and then in the class period we have get started on the lab. In other words, don't wait until later or until it's due or anything like that. I want you to get started very quickly on that lab and try to get that done. And really, it won't take long to do if you focus on it and get it done. So try to watch the video, go through the lecture, and then get started directly on that lab. All right, let's go and get started. So the first thing, the list of topics that we're going to cover today, we're going to review some stuff about the C preprocessor, and then we're going to look at preprocessor directives, and we're going to look at how to use the preprocessor with to create macros and use that. So let's go and get started. So the preprocessor in review is part of the C language compilation process. And essentially when a C language program gets compiled, the source code has initial operations performed on it by the preprocessor. In other words, it's kind of like this two-stage compiling process that starts with the source code that goes through the preprocessor and has operations done on the text of the source code itself, and then that gets moved on to the actual compiler. So the preprocessor handles all the directives by performing operations on the text of the source code before that goes to the compiler. And that's important. So it's kind of like a little text macro processing language in and of itself that's not part of the C language, what the C language compiler handles. It has its handled in that first stage. All right, so an example of that we saw before is like this pound include statement in this little program we have down here. Pound include standard io.h. That's a preprocessor directive. And what it does in this particular case is it causes the preprocessor to say, oh, there's a preprocessor directive. I'm going to go out and open this file, and I'm going to paste the contents of that file into this one in place of this directive. So it's kind of like cut this line out, replace it with the contents of this entire other file. So this is going to all get expanded, and then that whole thing will move on to the compiler for the compilation process. But notice it's editing the source code by adding another file in place of this line. And the main reason for that in this particular program, which we've said before, is if we're going to use this printf function, that's part of the standard library, the compiler has to know what that function returns, what it accepts as parameters, in order to create the code to use it properly and to check that we're using it properly. It has to know that. Well, we could type that in every time up here, but to save time from having to do that, we can just pound include standard io.h, and it'll stick that in the top for us. Now, the standard io.h has a whole lot of other stuff in it as well. It's unnecessary, but the compiler only cares about when it compiles, it says printf, hey, I have a definition for that. It was in here. And so it can tell that we're using that correctly. So even if we've defined things we're not using, that's okay. But if we tried to use this function without this pound include up here, the compiler would not know what this function looks like as far as how many parameters, what types they are, what is the return type, and so it could not compile this, or it would have to. There are things called implicit declarations in compilers where it will just make an assumption, but if it makes the wrong assumption, then the code might not work correctly. So this ensures that it'll also give you a warning if you do that. Okay, so to review the preprocessor a little bit farther, the preprocessor does some other stuff to the source code too. So for example, it's responsible for getting rid of all the comments. And what it does, if it finds a comment in your source code, it essentially replaces it with a single space character. So when you have a large comment like /* and multiple lines, // all that gets cut out and replaced with a space. It also deletes all \newline sequences, which are used for line continuations. So if you had a really long line in a C program and you wanted to, for readability, you wanted to break it up across multiple lines, you could actually use a \newline to go down and go to the, in other words, if you end your line with a backslash, then it'll take what's on the next line and move it up as if it was there. So it'll delete all those and put all those back together. It'll also use any of the predefined macros. The standard ones are like __, date, __. So you could actually write your code so that it knows what date it was compiled, or what file it's in, or what time it is, time of day. So you can get time, date, file. There are other ones as well. but it replaces all those with their expansions. And then also any preprocessor directives that you put in there, pound include, pound define, conditional compilation, and do that. So all of that gets done by the preprocessor, and then the resulting file gets passed to the compiler. So one of the ways you can think of the preprocessor as kind of preparing the source code by editing it and preparing it for compilation, preparing it for the compiler. All right, the preprocessor directives that we can put in to control this are all identified by starting with that pound sign. And the other thing to note is that when you write out that preprocessor directive line, you don't generally want to put a semicolon at the end of that line because they're not part of the C compiler. They are something else. And hold on just 1 second. I'm going to pause this. I will be right back. Okay. Sorry about that. I had a child care issue I had to deal with. Okay. So here are some preprocessor directives listed here. We're going to go through these, so I'm not going to spend a lot of time on them right now. But we're going to go through and look at those and talk about what they do. All right, so let's go and start with pound include. We talked about this last class, but I'm going to mention it again here just for completeness. But you'll notice that pound include, you basically list some file in there, usually a header file, but it could be any file. It could be another C file. It could be you could put a bitmap picture in there. That's generally not done, but you could do that stuff. You could put some text file there. It'll really just say whatever file you specify, it'll replace this preprocessor directive line with the contents of that file. And the angle braces around this, the kind of less than, greater than surrounding the file name, that tell the compiler to look in the standard include directory, which is a defined place for the compiler. And generally what's inside of that standard include directory are all of the header files for the standard library stuff in C, like standard.io.h, stdio.h. There are other ones as well, standard lib.h, math.h. Those will all be in kind of this standard location here. Now, if you want to use a header file that's part of your project, though, that's not part of the standard distribution of C, then you can use double quotes around the file name, the header file name. And that can be anything you want. You could also include a path in here. That could be a relative path or an absolute path. But essentially, the compiler will look in the same location as the file that's being compiled. It'll look in the project. It'll look in the source path on your machine. Or it could take an absolute path. A lot of times you'll have like relative paths that are used. So it'll say pound include and it'll like header file / another file.h or whatever. But the idea there is you can put those header files anywhere and still get to them by using the double quotes rather than angle braces like we have up here. And even though you can include any file, it's usually used to include the contents of header files. And header files contain defined types, defined constants, and function prototypes, which are kind of like the call signature of a function that tells how many parameters, what the types are, and what types it returns. And the reason that you have to have that at the top of your program is that allows the compiler to know what the functions look like as far as what types they expect and types they return, so it can generate the code that it needs to compile it. Okay, so one of the things that is important here, though, is include guards. And I'm going to mention these even though we haven't looked at some of the stuff we need for this. But looking at this, you'll note that it's sometimes possible to have the contents of a header file get included more than once. So imagine you have a project and it's got 2 or 3 different source files. And they all are including some header file. Let's say you made a game, and in that game you made like a structure, which we haven't talked about structures yet, but they're kind of like a group of data for a player. So inside of there you might have a structure that's like player data, and inside player data you might have the X coordinate, the Y coordinate, the hit points, the health, the experience points, the score, an armor class, whatever, all of that stuff inside of that structure. Well, that structured definition, if you tried to include that file twice, it would say you're trying to redefine it. It's already been defined. We already have something called this. You can't define it more than once, and so you get an error. So the way to fix that is to put, when you create a header file, is to usually wrap it in what's called an include guard. So in other words, inside of the header file itself, you would have this line if ndef, my header file, you give this a name, like in our case, it might be player data _h. And then what this does is, if it says that what if ndef is doing, which notice that's another preprocessor directive, that's saying if it's not defined that we have that header file included, then go ahead and define it. And then we put the contents in here for our player structure, whatever that we've defined, and then our end if, which ends that kind of if ndef. So in other words, if this is not defined, go ahead and define it. So that way it will only ever get defined once. So the first time it encounters this, we'll say, hey, that's not defined yet. I'll go ahead and define it, and then here's the stuff that we want to define. And then the next include that it comes across and says, oh, that's already defined, so I'll just skip over all of this. So that way we can guarantee it will only get used once. We'll come back to this later in the semester once it makes a lot more sense what we're talking about with header files. But for right now, just notice that if you create your own header file, then you probably want to have something like this around it. And in fact, if you are in like code blocks as the IDE and you say make a new header file and give it a name, I believe it'll add this template for you with the include guards already there. It's just good practice to do that whenever we are creating our own header file. Now, you don't have to do that, but it can be helpful for things getting included more than once. All right, so let's go through some of these preprocessor directives. We'll go through them a few at a time here. We'll start off with pound define. We've looked at that before, but I want to spend a little more time on it today. So looking at that with pound define, you'll notice that it allows you to define constants and macros, which are kind of a little bit look like functions, but they're really not. It's just kind of, again, just editing text. So there's kind of two types of those. There are what are called object-like definitions, and then there are function-like definitions. Now, an object-like definition, you can essentially think of that as here's an identifier name that we're defining, and here's the text that replaces it. So in other words, when the compiler sees PI, capital P, capital I, as an identifier in our source code, it's just going to cut that out and replace it with this text over here. And you can tell when you have an object-like pound define because there aren't parentheses after this. It's just an identifier name. And so in other words, it's just a fancy definition of a cut and paste operation. We say whenever you see pi, replace it with this number. And it's really not even a number, it's just these characters. So when I see pi in the source code, replace it with that before it goes to the compiler. And notice that can be used to make your code a lot more readable. That rather than having to type this out every time, or maybe people not knowing what it is, you can define your own textual version of it. And then when somebody reads the code, they'll see pi rather than a bunch of digits. The other type are these function-like ones, and those allow for more complex substitution in that line. And the way they work is like this. So down here, pound define, rad _2_deg. This is like radians to degrees. And notice that's allowing me to put this formula into my code, but I can put it in as rad _2_degrees. And then, so if I were to put, for example, like pi in here, so 3.14159265, if I were to put that in the parentheses, then that'll end up giving me 180 when it calculates the value coming out of this. So the idea here is it allows me to clean up my code and have this rather than having this formula every time. But really, what's going to the compiler is just the formula happening every time. But the way this works is it's not only doing the substitution of rad to degree with this, but then it's taking the thing in parentheses where there's this x, and it's substituting that text, whatever we typed in there, it's substituting that in for the x over here. So in other words, this x is being pasted into there, and then this whole thing is being pasted in for wherever that line was, or that part of the program that was using that macro that's defined. And that can be a really cool, powerful thing once you get, at least once you get used to it. So we're going to look at a few more of those here in just a minute. But before we do that, let's look at a couple other things here. Undef. Undef allows me to undefine something that's previously been defined. So in other words, if I have a pound define for something in my code and I want to redefine it, it'll give you an error if you try to redefine something that's already defined. But if you undefine it first, then you can then redefine it with something else. So in this case, we could do pound undef pi, and that macro will now no longer exist for the source code after the undef. So if we do undef something, we can then redefine it somewhere else in the code if necessary. And that one doesn't get used a whole lot, but it is useful to know about that. All right, now conditional compilation directives use this pound if. And we actually saw one previously back, right there, that if ndef. We'll talk about that in a second. But conditional compilation allows the compiler to either keep things in the source code or take them out of the source code based on the preprocessor directive. So in this case, for example, we might say pound if, and then we have something like log level greater than or equal to 2. And notice that log level here is not, that has to itself be something that's pound defined. That's not like a variable that's being used. That has to be something that's part of the preprocessor as well. So we could have a definition somewhere where we say pound define log level equal 2, or pound define log level, or I shouldn't say equal, pound define log level 2, pound define log level 4, whatever. But this allows me to say, hey, if the log level is greater than 2, then we print out this kind of error. Otherwise, we leave this printf completely out of the code. And you'll notice that this is not something that happens at runtime. It's not a runtime if statement like you're used to in programming. This is actually deciding to remove that code from the source code or leave it in the source code. And that feature can also be used to make programs cross-platform. An example of that is what we have here. In this case, we say if def underscore underscore Unix underscore underscore, which is most Unix systems, the compiler has that defined. So you would say if def underscore, so in other words, if I'm on a Unix system, then I include this source or this header file. Otherwise, if I'm on a Windows 32 system, which would be a Windows-based system, then I include this file instead. And that can be used to make your code cross-platform. In other words, the same code, if we compile it on a Unix system, it'll put the right thing in. If we were to compile it on a Windows system, it'll put the right thing in. And you don't just have to put these pound includes in here. You could have different code. So for example, on a Unix system, the way that you interact with something might be different than the way you do it on a Windows system. So you could have the code in your project that deals with a Unix system and the code for dealing with a Windows system, and you could have another one for Mac, and you could have another one for some other Android device. So it allows you, and notice it has, since it has this else if, as pound elif, you could have as many of these as you want, and you could also have an else. So that can allow a single code base to support multiple platforms. And the other thing that I've used that a lot for is to have a single code base that supports multiple products that you can build. So you could say, hey, if this is a wireless sensor we're compiling for, then include the code that talks to the wireless module. If it's not a wireless sensor, then leave that code out. Or if this is a program that the client has paid for a 32 user license, then add this extra feature set into that. Otherwise, leave it the free version that only allows for 2 users or something like that. And you can do that with this stuff without having to happen at runtime. In other words, the project you build, you can set up the pound defines the way that you want it to build, and then build it. Another common use of this if thing is for debugging purposes. Kind of like back here where we had that log level thing. You could say if def debug mode, then include all this extra stuff that prints things out or logs things to a file or whatever. And then once you've debugged the whole thing and you want to turn it off, rather than having to comment all those debug things out, you just take out the pound define for debug mode and say, don't define that. And then all of that code gets dropped out of the executable, the version that gets compiled. So this can be this conditional compilation can be a very powerful thing to understand. There's also this directive pound error. It's a preprocessor directive, and all that does is if it encounters that, it'll basically stop the compilation, and it'll put that error into the kind of the error log or the error output of the compiler. So you could say, hey, if it's defined Win32, then this program can only be compiled in one. That should be if ndef there. Here, I'm going to fix that very quickly here. Oops. Go back. So this should be if it's not defined Win32, then we do that. So that will basically say it can only be compiled on Windows systems. So if we're on something other than Windows 32, it won't let that compile. Oh, let me go back to normal mode here. There we go. Okay. Now, those pound error things are almost always used within some conditional compilation section inside of an if-def or an if-end-def or an if and a end-if. So keep that in mind. Now, let's go on to the next thing here, and I'm going to pause for just a second here. Okay, now, the next thing that I want to do here is look at using those macros for, oops, let me go back a second here, is using those macros for kind of these function-like purposes. And it's important to note that these aren't really like functions that get called. So here's an example. We're using pound define squared, and we have parenthesis x, and then after that we have parenthesis x times x. So what that's going to do, remember, is anytime we use this squared macro, it's going to do a substitution where it cuts that out. So down here in my code, squared parenthesis 10, it's going to cut that out, and it's going to replace it with this stuff over here. And the stuff over here, it's going to take whatever was in the parentheses, in this case 1, 0, it's going to put those in there and have 1, 0 times 1, 0, that whole thing in parentheses. And that's going to get stuck in place of this whole thing. So let's look at how the substitution would happen. So here's the macro, the function like macro. Here it is being used in the code with the 10 in parentheses. That's going to get cut out and replaced with this pattern here with the x substituted. So the 1, 0 was in the parentheses, that goes in there and there. So this is what gets pasted into the code. So what's going to get compiled is just parenthesis 10 times 10 end parenthesis. That's not calling a function, it's all right there. And one of the advantages of macros, notice, is that can be very efficient because we're not calling a function. It's just pasting that calculation right in there, even though it looks like we're using it like a function up here. It's just pasting it right in like that. Now, one of the dangers of that I want to point out, and I think this is important to point out, is that the way we defined this here was actually kind of dangerous. And I did that on purpose to point out why it's dangerous. So why is that dangerous? Well, it worked fine back here when we did that. 10 times 10 is really 10 squared. That makes sense. But notice that since it's just doing a text replacement on those things, that if I were to use it like this, so a different usage example would be squared 5 plus 5. Now, if we plug that in, you might say, well, 5 plus 5 is 10, so that should be the same thing. But remember, with macros, it's editing the source code. It's not really doing the 5 plus 5 and getting 10 and then passing that. And it's just taking whatever's between the parentheses and pasting that into the source code. So let's look at how that replacement will work. So squared 5 plus 5, we take the 5 plus 5, stick it in for x, and then we get 5 plus 5 times 5 plus 5. But notice the result is 5 plus 5 times 5, which is 25. So now we're at 30 plus another 5. So that's a result of 35. So we think we're squaring 10 here, but we're really doing this other thing that's unexpected. But if you look at your source code, it looks like that. The source code does not look like that should be giving you 35. And that can be a big problem if you misdefine your macros like this. So what's the solution for that? And the main solution that I use a lot for that is to, anytime you have a parameter that's going to be used in a numeric context, always just put parentheses around it in the macro over here. And if we do that, notice that that fixes things like this. So we still say squared 5 plus 5, but now notice when that gets plugged in inside these parentheses. So now we get, this is the code that gets generated. So parenthesis 5 plus 5 gives 10 times parenthesis 5 plus 5 is 10. 10 times 10 is 100. So now we get the right answer from that. And that's anytime you have one of those function-like macros, it's usually a good idea just to put the parameter here in parentheses wherever it's used to guarantee that you'll always have the order of operations not mess things up when it gets expanded later. And you can't necessarily predict how everybody's going to use that, so just wrap it in parentheses and that will usually solve those problems. Okay, now one thing, the macros can be named anything that a valid C language identifier, like a variable or a function, can be named, meaning start with an underscore or letter, only consist of underscores, digits, and letters. But by convention, C programmers have kind of settled on this concept of when you name a macro, whether it's a object-like macro or a function-like macro, always just use all uppercase letters. And the reason for that is that way when you see it in your code, you know that's not a variable, it's not a function, it's a macro that's defined somewhere. So for example, if we named like max players all underscore, you might think that's a variable. But if it's all uppercase like this, then you know it's a macro if you follow that sort of convention. And that most C programmers will use all caps on macros, and the reason being you can easily identify that when you see it in the source code. So you'll tend to see like max underscore players, and then a number over here. All right, now one other thing to kind of wrap things up, and then I'll turn you loose on the lab time here, is here's a really important bug warning. And I'll tend to do this throughout the semester when I come across something that's a common pitfall that I see programmers make and cost them time or things not to work right. I'll try to point those out, and I'll always like identify it with bug warning. And then we'll talk about why. But the idea here is there's a tendency to get used to typing a semicolon at the end of your lines when you're programming in something like C. And the disadvantage of that is that notice that when you say pound define, in this case feet to inches, and you put this X in parentheses and you put that 12 and you put the semicolon on the end, the problem is that that's not going to give an error because you have a semicolon on the end, because it's just cutting this out and pasting this in place of it. And when it pastes this stuff here in place of that, that's going to include whatever it is all the way up to the end of the line, including that semicolon. So in other words, if we use that macro in our code, we say printf 3 feet is %d inches. And as a reminder of the way printf works, this %d is a format specifier for a decimal integer. This number is what's going to get plugged in place of that. So it's going to, ideally, when we run this, it'd say 3 feet is 36 inches. And it is going to work. It is going to expand that. But notice when it expands it, it includes the semicolon. And the semicolon is now going to be stuck in there as the end of statement, which is going to happen prematurely. So the compiler is going to give you some error that basically says when there's an open parenthesis and it got to the end of the statement without the closed parenthesis. So it's going to give you an error that says something like, hey, this line of code, meaning this one up here, has a missing parenthesis. Or it'll say unexpected semicolon, expected parenthesis, or something like that. So the compiler is not going to be able to make sense of this because there's an unexpected semicolon right in the middle of what was this printf statement. So it's going to give you some kind of error message about that. But it's going to give you the error message on this line up here, and you're going to look at that like, well, the parentheses match and there's only one semicolon. I don't know why I'm getting an error. And the reason you're getting there is because you had this badly defined macro that had the semicolon at the end. So kind of the short of this is do not stick semicolons at the end of those macros unless you intend to specifically. So don't just get in the habit of semicolon at the end of the line. And if you get a weird compilation error and it's pointing at a line like this that has a macro in it, and you can't figure out, there's nothing, it doesn't look like there's anything wrong with that line, go look at the macro because there's probably something wrong with that. For example, you could leave off a parenthesis accidentally or have something malformed here, but the place it'll give the error is on the line where you use the macro, not on the line of the macro itself, because this is not part of what goes to the compiler. It's just something that gets cut and pasted in place of wherever we use that macro. All right, so be cautious there. Okay, and that's pretty much all we're going to do today as far as the lecture. Go ahead and work on Lab 1. Lab 1 has multiple programs to work on. They're relatively simple. You're going to play around a little bit with the preprocessor, use pound include for some things. You're going to play around with the printf kind of function, part of the standard library. And then you're going to do something kind of fun with the preprocessor and get it to do something else. Now, one thing that I do want to do before I turn you loose here is let's just take a quick look at that lab assignment. So let me bring that up so we can see it together here. And let me turn that on. Okay, so here's the lab assignment. Let me zoom in on that so you can see it a little better. All right, so notice that you have 3 programs that you're going to write for this lab. The first thing about this that I'd point out is, well, other than the due date, is that you're going to write 3 individual programs, and I want you to use that CodeBlocks IDE for the assignment. In other words, go ahead and install CodeBlocks. Go to codeblocks.org. And on codeblocks.org, you're going to download and install the one. Make sure you get the one that says the Windows installer if you're on Windows, and make sure you get the one that says MinGW on there, because that's the one that includes the compiler. Unless you already have a GCC compiler, already have the compiler installed, the C compiler installed, go ahead and get the one with the compiler, because then when you install that, it'll give you everything you need to create that. Now, when you go to create that project, what you ought to do is go to File, New Project, and then, and here, let me just bring up CodeBlocks so you can see it real quick. All right, so here's what CodeBlocks is going to look like. And notice CodeBlocks is cross-platform, meaning if you're on Linux or a Mac, you can still use the same tool, and it will still work in the same way. Okay, so here's what CodeBlocks looks like when it comes up. So what I would say, what you need to do here to create a new project is say File, New, go to Project. And then for creating that new project, what I would suggest you do is do this kind of console application as the default, because that's what we're going to be doing for right now. So just pick that, say Go. And now it'll ask, go through this wizard, and you can say it's going to be a C project. Say Next. And then here, give the project a title. So I would call this like Lab 1A. Next. And then Finish. And now it's going to go ahead and give you make the project for you. Now, under Sources over here, there's this main.c. Go ahead and click that. Double click that. It'll bring it up in the code editor. And notice that in this console application, it kind of built or added the skeleton for this for us. You could have done an empty project and say create a new source file and added that. But after you've created this, now to try it out and compile it, just click this Run button up here at the top, or you can go up to Build and click Run under that. Or you can do Build and Run. But in other words, when you click that play button, it says you need the project has to be built first. You want to build it now? You can say yes. It'll build it and run it. Now, notice it brings that up in that console window. Hello world. There it is showing the stuff. Now, if you have errors in your code, it's going to show up down here. And let me go ahead and close that real quick. But it'll show up down here. If it compiles correctly, it'll say, looking in this window down here, you'll see that 0 errors, 0 warnings, and it'll show you how long it took to actually compile it. So if we want to change this program and get it to do other things, we'll just edit it up here. So up here we'd say, well, you know what? I want to do hello \n \t world. Try it again. Click play. Oh, I need to do build and run. Hold on a second. So let's do build and run. Let's do that one. Build and run. There it is. And now I notice I get a different output. Hello, new line, \t world. And then so you can kind of go back and forth between making changes here, trying to compile it. Now notice if I have an error in my code, let's say I leave off that semicolon accidentally. And coming from Python, as some of you are, you're going to forget semicolons. So you're going to get these errors. Build and run that. You notice it didn't work. It had an error. And if you look down here in this little build messages window, you'll notice that it says error expected semicolon before return. And so when you get an error message, read what it says and try to figure it out. And you can come up here and go back and say, oh, I forgot my semicolon there. Let me add it on. And then build and run again. And now it's back to working again. So that's going to be the process you're going to use for the development of this stuff. And what I want you to submit when you go to turn this in is you'll notice that in this code here, if I do file, save file as, You'll notice that the place that it will generally put it is in your documents folder under the name of the lab. If you want to, you could make your own thing, like for the class, your own folder, and just stick everything in there. But what I need submitted for this is not, at least not right now, I don't need the entire project directory submitted. All I really need is the name of the C files, the source files submitted. Later on, it's going to be easier to do that. But if it's easier for you, notice if I go back up to where that lab 1A is, right there. If it's easier for you, you could drag the whole thing into a zip file, lab 1A, lab 1B. Or if you want to, you could actually delete this bin and this OBJ. Those are actually files that get created when it compiles it. So you could get rid of those and only give me the main in that zip file. And that will make the zip file much smaller. Because notice in the object file here, you have actually, all right, nothing is showing up in there. Bin. Oh, this is looking for this file type. Let me switch the file type here to all files. So you'll notice that inside the bin directory, that's where the executable gets built, that it actually runs. And in the object directory and debug, that's where the object file gets built before it gets linked. And so if you when you submit those, you'll just have extra stuff that I don't need in order to grade it, but that's okay. So if that's easier for you, take the whole thing, drag it in the whole project folder, this lab 1A folder, drag it into a zip file, and then essentially turn in that zip file with all 3 of the projects required for the lab. Now, the first program should be relatively easy. The second one should be relatively easy, except for the second one. It says, I want you to rewrite it so no pound include directives are used. And the way that you're going to do that, here, let's go back and look at, well, I just closed code blocks. But remember it had that pound include at the top? And the only reason we need that is for that printf statement. So what I want you to do is find the place on the drive where the printf statement has its function prototype in the standard io.h. So in other words, you might go to where the compiler is installed, search for stdio.h, search for that file, open that up in like a Notepad++ or Notepad or some other text editor, search for the printf function prototype in that, cut that line out, paste it into the top of your program where the pound include used to be, and then recompile it. And if you've got the right line and put that in there correctly, then you'll have the right thing. And as a quick example of that, here, let me bring code blocks back up for just 1 second. This is unfortunately slow when I'm running on battery. And let me reopen that project. It's probably also running on battery while recording is taking some time. All right, so there's recent projects, lab 1A. So in other words, what you're going to do, and we really don't need standard lib in here right now, so I'm going to take that out. But you're going to take this line and take that out. So you're going to cut that out. But we want to open this standard io.h file. So we need to figure out where that is on the drive. Notice it's in the standard include directory. And one of the ways you can figure out where that is, if you go to settings over here, go to compiler. Toolchain executables. Notice here it's showing you the compiler's installation directory. So if we go to that, C program files, code blocks, min.gw, that's where things are. And if you look under search directories, or actually compiler settings, yeah, it's under toolchain executables. But that shows where the files actually are. So if we go to that location, and let's actually do that real quick. Let me just bring up a file explorer and we'll try to go to that. Oops. So, I'm on the wrong window, so you can't see what I'm doing here. So, I'm in program files x86. I'm going to go into code blocks, and then inside of there's this min-gw directory, and then you'll notice inside of there is this include directory. That include directory is the standard one where all the include files are. So inside of here, you will see stdio.h. That notices a whole bunch of stuff in the standard library. So there's stdio.h. I'm going to right click that and say edit with Notepad++. And now you can see all of the stuff that is inside of that standard.io.h header file, but the only thing we really need from that is let me move this so we can actually scroll through that. But the only thing that we need from that is the printf function prototype. So what you'll do is you'll search through this, find where the printf function prototype is, and let me see, Control F, printf. Okay, that's fprintf. Okay. And here's the function prototype for that. So you'll just need to copy that into the top of your program, and then compile it with that in there. Now, one thing to keep in mind is function prototypes end with a semicolon at the end of the line. So you'd copy that line we just looked at in there into the top of your program in place of where the pound include was. And let me go back to that. Code blocks. Cancel that. So you'll paste that printf function prototype in the top of this and then compile that. And you'll notice that this isn't necessary except to get that printf function prototype in the top of your program. All right, now version 3, program 3, we're going to be rewriting, making a set of macros to make Python or make C language act a little bit like Pascal. And Pascal, rather than having curly braces, it has begin and end, and rather than printf, it uses write and write line. And essentially what the difference here is that write will write something without a new line. Write line will automatically add a new line at the end for us. Now, the big question here is you might say, well, just pound define write as printf. That'll solve these ones. But how do you get write line to automatically add a new line on the end? Well, remember that in a macro, when you're pound defining that, it's the whole thing up till the end of the line. So you could actually have printf the first part of that, and then after that, put a semicolon, and then printf just quote, double quote, \n after that to go to the next line. So you could actually have one macro substitute something in for a line that has multiple statements in it. So you'll have to play around with figuring out how to get it to do that. But the idea here is to show you the power of the preprocessor. So you're going to add pound defines up here. That pound define, for example, begin as an open curly brace and as a closed curly brace, write as printf, write line as kind of these two printfs, one that's putting a new line, one that's printing the string. But notice that these are going to have to be function-like macros. These are going to be object-like macros for these. But it's really not a lot of work. There's just a few pound defines you need up here. But that's all you should have to do for that one. Okay, so get those done. You should be able to get those done today. Go ahead and work on that and see if you can get that done today. Get code blocks up and working. And that's all for today. So everybody stay safe. And keep in mind there may be a quiz coming up shortly as well. So just be ready for that. And that's it.